Modulation is the heart of communication system, transforming raw information into a format suitable for transmission. In free space optical communications, we primarily deal with two modulation techniques, baseband and subcarrier modulation. So let's first speak about baseband modulation. This is the simplest form of modulation, where the signal directly modulates the drive current of the LED or laser, alternating the intensity of the optical carrier. It's a straightforward and cost-effective method, but it's limited in bandwidth and can suffer from distortions at higher frequencies. On this diagram shows the baseband modulation process. We have the input signal is applied to the transmitter. The transmitter directly modulates the optical signal. The modulated signal passes through the channel. At the receiver, the received information is extracted from the optical signal. While on the other hand, subcarrier modulation, this technique offers a more sophisticated approach. The incoming signal is first mixed with a locally generated coherent carrier signal from a local oscillator. This creates a modulated subcarrier, which then modulates the optical carrier. Subcarrier modulation offers improved performance in terms of bandwidth, noise immunity, and linearity, making it suitable for high-speed and long-distance FSO links, as you can see on this diagram. The choice between baseband and subcarrier modulations in free space optical communication depends on various factors, including required data rate. Subcarrier modulation is preferable for higher data rates. Link distance. Subcarrier modulation offers better performance over long distances. Cost and complexity. Baseband modulations is simpler and more cost-effective. In conclusion, understanding this modulation technique is crucial for designing efficient and reliable FSO communication systems. By carefully selecting the appropriate modulation scheme, engineers can optimize FSO links to meet specific requirements at various applications. Modulation is the process of encoding information onto a carrier wave for transmission. In free space optical communications, we employ two primary methods, internal and external optical source modulation. Well, let's first of all see internal optical source modulation. This technique involves directly modulating the light source itself. In the case of a laser, diodes, this is achieved by varying the drive current, as is shown in the diagram. A DC bias current keeps the laser operating above its threshold, and a modulating voltage signal is superimposed on this bias to vary the lace output intensity. This simpler approach is cost-effective but limited in its bandwidth. We can have also external optical source. For higher bandwidths and more demanding applications, we turn to external modulation. This involves a separate modulator plate placed outside the laser, as illustrated in the diagram. A common type is the lithium niobate modulator, which alters the light's phase or intensity based on applied voltage. External modulator offers superior linearity and bandwidth, but it adds complexity and cost to the system. Choosing the right technique, the choice between internal and external modulation depends on several factors. For example, bandwidth requirements. Internal modulation is sufficient for lower data rates, while external modulation is necessary for high-speed links. Internal modulation is generally more affordable, while external modulation requires additional components. External modulation can handle longer distances with less signal degradation. Internal modulation is simpler to implement, while external modulation adds another layer of complexity. By understanding the trade-off between these techniques, engineers can select the most appropriate modulation method for a given FSO system, ensuring optimal performance and reliability. Modulation is the process of encoding information onto light wave for transmission. In free space optical communications, two fundamental techniques used are on-off keying, OOK, and pulse position modulation, PPM. So let's right now explore each of those. First, on-off keying. On-off keying is the simplest form of modulation, where the presence of light represents a binary 1 and the absence of light represents a binary 0. This technique is analogous to turning a flashlight on and off to transmit Morse code. In the diagram, the top figure shows that for a binary input of 1, the laser is switched on for an entire bit duration. For a binary input of 0, the laser is switched off for the bit duration TB, as shown in the bottom figure. While OOK is straightforward and easy to implement, it has limitation in bandwidth, efficiency, and is susceptible to noise. We also have pulse position modulation. Pulse position modulation is a more sophisticated technique where information is encoded in the position of an optical pulse within a time frame. The diagram illustrates that for binary input of 1, the pulse is transmitted in the first half of the symbol duration, TS, and for binary input of 0, it's transmitted in the second half. PPM offers better performance in terms of power efficiency and noise immunity compared to OOK, but it requires wider bandwidth. Well, choosing between OOK and PPM. The choice between OOK and PPM depends on the specific requirement of the FSOC system. OOK is suitable for shorter distances and applications where simplicity and cost effectiveness are priorities. PPM, on the other hand, is preferable for longer distances and scenarios where power efficiency and noise immunity are critical. Understanding these modulation techniques is essential for designing efficient and reliable FSOC communication links. Each technique offers a unique set of advantages and trade-offs, and the right choice depends on the specific application and system requirements.